Hi, Assalamualaikum warahmatullahi wabarakatuh. In this video, I'm going to continue on with the idea of moment generating function and how it can be used to generate moments such as the mean, and also use it to come up with the variance of a random variable. So in this particular example here, we have our random variable y having a Poisson distribution, which is described by this probability distribution right here, and you are asked to show that the moment generating function is given as such, and after that you are required to use this moment generating function to further demonstrate that the mean and variance of y is lambda. So without further ado, we are going to start off with demonstrating that the MGF, moment generating function, is indeed as such, and our starting point is going to be finding the expected value of e to the t y. So y is our random variable, and we know that our random variable y here is a discrete random variable, and therefore you are going to deal with the summation process. Right here is e to the ty, and here will be the probability distribution of y, and we know that if y is a Poisson distribution, y can take values from 0, 1, and it goes on. Therefore, y from 0 until infinity. So that's the starting point. Now we're going to substitute this with appropriate probability distribution. So here it will be y equals to 0, infinity, e to the ty. Over here is lambda y, e negative lambda over y factorial. Next, what we can do is we can try and recognize the constant and take it out of that expression. So here is negative lambda. It doesn't depend on y, so we know that this is a constant and you can take it out. So e to the negative lambda, and this is the rest of the expression given as such. Now notice that here we have y, and over here also we have the same alphabet here, y. Okay, we have the same value where you can actually end up combining these two terms together. So that's what we're going to do next. Okay, so here we will have e negative lambda, and this is y from 0 to infinity, and we're going to combine that with lambda e t y factorial. So you can see that these two terms here are now combined under one roof. So here y is on the outside at the top. Okay, now the result of this, according to the power series expansion, the result here is just going to be equal to e lambda et. Okay, so the result is going to be e negative lambda times e lambda et. So let me just write down a little bit about the idea of power series expansion. So the power series expansion, as an example here, when you have something that looks like this, x to the n factorial, and here is n from 0 to infinity, the sum of these infinite terms is going to be equal to e to the x. Okay, so that's the result of power series expansion. Therefore, so notice here we have n from 0 to infinity. Over here we have n and n. So notice the similarity between the result here and what we have over here. Over here we have y from 0 until infinity, okay, which matches what we have here, and from 0 to infinity. Next, y appear on this side, as such n appears at this part here with n factorial. Y appears here as the something to the power of y. So here we have x to the power of n. Therefore, if here is x and the answer is e to the x, therefore here the answer is going to be e to lambda e to the power of t. So this term here will be the part at the top. So basically we are just comparing the situation that we have over here with the established result of power series expansion. All right, maybe I will talk more about this power series expansion in the next video, but for the time being, the result that we get over here comes directly from the established result of power series expansion, which is given here. Okay, right, let me just erase that part. Okay, so now what we are left with is we just need to simplify the expression that we have here, and it becomes, well, if you simplify that, this become e lambda e t minus lambda. So this is how we can write the expression above here, and you can factor lambda out, e lambda et minus 1, and this is the result that we are required to demonstrate. Okay, so that's it for the first part. Now we are going to use the result that we have here to try and demonstrate that the mean and variance of y is lambda. So we all know that the mean of y is just the expected value of y, and in order to find the expected value of y, I can use the MGF. So MGF is given as such. Okay, so this is the MGF. Okay, that is the MGF. What I need to do is, since I would like to find the expected value of y, I need to differentiate it once. Therefore, if I differentiate this one time, the result is going to be, we are going to apply the chain rule. So the chain rule says first you have to differentiate all this thing, and then you're going to differentiate the inside of it. Okay, so first of all, let's talk about differentiating the outside of it. So what is the result if you differentiate e to the power of something? You will get back that particular result. You will get back e lambda et minus 1. So this is the result that you get when you differentiate the outer part. And then if you focus on differentiating the inner part, if you differentiate that with respect to t, well, the result that you will get is going to be lambda e t, because when you differentiate lambda negative 1 here, it will be 0, so minus 0. So that's the thing, and that can be simplified as e lambda et minus 1 times with lambda et. If I substitute t to be with 0, the result here is going to be, well, e lambda, e to the power of 0 is 1, so 1 minus 1, lambda e to the power of 0 is just 1. So we can simplify that to be 1 minus 1, 0. So e to the power of 0 is 1, lambda 1, and this is equal to lambda. Therefore, the expected value of y is just equal to lambda. So that's the second part of it. Next, we are going to show that variance of y is also equal to lambda. So this is what we need to show. And we know that variance of y can be obtained if you consider this formula, ey squared minus ey, and you square it. Well, the expected value y has already been obtained, and so in this part you need to find what is this value over here. And again, we can use the already obtained MGF. So here is our MGF is given as such, e lambda et minus 1. So this is our MGF. And then the first derivative is just what we have obtained right here, which is e lambda et minus 1 times with lambda e to the t. So this one, that is the first derivative. But since we need to find y, expected value of y squared, that means you have to find the second derivative. So the second derivative can be obtained when you consider differentiating this function here. And for that purpose, I think we can consider this to be f, and this one to be g, and we can use the formula, which is fg prime plus gf prime, in order to obtain the derivative of that function. Okay, well, so let's get on with it. Now what happened is f is this thing, so we're just going to write down e lambda et minus 1, so that is our f. So g prime, differentiate this, you will get lambda is a constant, so it is maintained as it is. Differentiate e to the power of t, you will get back e to the power of t, so that is f g prime. Next, what we can do is plus g is this guy over here, lambda e to the power of t, and f prime. So f prime is this thing, we need to differentiate this. This is our f, differentiate this, you will get, again, you need to consider differentiating the outer part. The outer part, when you differentiate e to the power of something, the result is going to be e to the power of something, so it's going to be e lambda et minus 1, so that's the result. And you need to differentiate the inner part, which is this one, just this one, and the result is going to be lambda et minus 0, so that's the result. Okay, and what we can do next is we can substitute y t with 0, and the result is going to be e lambda e to the power of 0 is 1 minus 1, lambda e to the power of 0 is 1 plus lambda e to the power of 0 is 1, and then e lambda e to the power of 0 is 1 minus 1. This one is lambda e to the power of 0, which is 1 really. Okay, that's it. Simplify that, 1 minus 1, 0, so this is 1 times lambda plus This one is lambda e to the power of 0 is 1 times with lambda e to the power of 0 is 1. So the result is lambda plus lambda squared. So here is the dot. Okay. It looks ugly. Okay, let me just erase this and make it look a bit proper. Okay, so that is the result of this guy that we are looking for. Now variance of y, therefore variance of y is just ey squared minus ey, and you square it. Ey squared is this guy, so lambda plus lambda squared minus ey is lambda, and you square it. So ey is lambda and you square it. Therefore it can be easily seen that these terms can be cancelled out, and so variance y is equal to lambda. Okay, that's all for now. Thank you very much for watching.